section 7.5. We're going to talk about matrix operations. Today we're talking mostly about addition and subtraction. So, in our book, and what the kind of the standard way of writing matrices is we use an uppercase letter. So we're going to use A, B, C, whatever, uppercase letter, or we put the elements, just a representation of the elements of the matrices in brackets. So this is how we would refer to matrix A. So this would be matrix A. This is how we do this. And remember, with our elements, Aij is an element of A, and I refers to the row, and J is the column. So when we put brackets around the element, so some element, then that refers to the entire matrix. I think you have the wrong. This person is not. Okay. So the Aij by itself is an element. Aij in brackets refers to the entire matrix A. First thing we want to know is when matrices are equal. First off, matrices are equal if we need several things to happen. One, they have to be the same size or the same order. And when we said size or order, remember we talked about an m by n matrices, a matrix. So they have to have the same size, they have to have the same order. And each corresponding element is equal. So the way we write that in symbols is if A and B, matrix A and matrix B, are both m by n matrices, matrix A equals matrix B if each element Aij equals Bij for I from 1 to n, m, and j is 1 to ... to n. So we're saying we're matching up the corresponding elements, and each one has to be exactly the same for our two matrices to be equal. So just like we talked about with vectors, when we talked about complex numbers, we matched up the real part, we matched up the complex part, we matched up the x component, we matched up the y component. Matrices, the exact same idea. We have to match every single element in the matrix for the two to be equal. So, questions on when matrices are equal. Pretty easy idea. Well, now we want to talk about adding matrices. Well, when we add matrices, they have to be the same size or same order. It's the only time addition makes sense. and we add the corresponding elements. So we're going to say A plus B equals the matrix Aij plus Bij. So we're just going to add corresponding elements. It's kind of intuitive idea of addition. We're just adding each, just like we added matrices, just like we added vectors. We add the x components and add the y components. We add the real portion, add the imaginary portion. For matrices, we just have more pieces, so we add the corresponding pieces. So, and again, one important thing to remember is they have to be the same size or order. So let's look at a quick example. So if we wanted to add the matrix 2, -5, 4, 3, and we're going to add that to 8, -9, 1, -3. Just going to add the corresponding parts. 2 plus 8 is 10. -5 minus 9 minus 14. 4 plus 1 is 5. 3 minus 3 is 0. So that would be our sum. If our matrices are bigger, we just have more individual pieces to add, but they have to be the same size. These are both 2 by 2, so we can add them. One is 2 by 2 and one is 3 by 5. Doesn't make sense to add them. Addition is not defined if they're not the same size. Thanks, Don. Pause this really quick. Oops. And you were here for the quiz, right? All right. So the next thing we want to talk about is, well, before we go on, questions on adding matrices. Okay. Scalar multiplication. So when we were talking about vectors, what did we mean when we said we had a scalar? What are we talking about with a scalar? Just a number. Scalar is a real number. So we want to know how we multiply a matrix by a scalar. So we're going to say A is a matrix. C is a scalar. So we're going to say C times A. And all we're doing to multiply a matrix by a scalar is multiply each element by the scalar. So nice and easy. Just multiply every element by whatever our scalar is. So this gives us a convenient way of talking about subtracting two matrices. So we can say A minus B is A plus -1 times B. And we can also write that as A plus -B. So we can think of, just like we can with real numbers, we can think of subtraction as adding the negative. So this gives us a way of thinking about, just a different way of thinking about subtraction. So we can define subtraction as adding the negative. So questions on scalar multiplication? All right, so let's look at a couple of examples having to do with scalar multiplication. So let's say that A, matrix A, is this matrix 4, negative 2, 3, 1, 8, negative 6, 5, negative 7, 1. And B is this other matrix, negative 1, 6, 2, 4, negative 3, 5, 9, negative 2, and 3. Now we're going to do two things here. First, we want to find 2A. Find 2A, we just multiply every element in matrix A by 2. So we get 8, negative 4, 6, 2, 16, negative 12, 10, negative 14, 2. So there would be our matrix 2A. Pretty easy. A minus B. We could do the opposite of B, negative B, or we can just think of subtracting. Give us the same thing. So we're just going to subtract corresponding elements. 4 minus negative 1 is 5. Negative 2 minus 6 is negative 8. 3 minus 2 is 1. 1 minus 4, negative 3. 8 minus negative 3 is 11. Negative 6 minus 5 is negative 11. 5 minus 9, negative 4. Negative 7 minus negative 2, negative 5. 1 minus 3 is negative 2. So there's A minus B. Questions on how we came up with that? So just adding and subtracting. What we're leading up to is to be able to talk about equations that have matrices in them, and we'll deal with the matrices, like I said at the very beginning, as one single thing. Rather than dealing with every single element, we can deal with the matrix as one single thing, do some manipulation with the matrices, and then at the end of the problem, then talk about the individual elements. So it'll let us solve problems in a little different way. All right. Our properties. Of matrix operations. So these are just some rules about how we can combine matrix addition, basically matrix addition and scalar multiplication in different ways. So first off, I'm going to say that a large 0 is the zero matrix. And it's a matrix with 0. Every element is 0. And it's important to remember that the 0 matrix doesn't equal the number 0. 0 matrix is a matrix with zeros in each place. So a 3 by 3 0 matrix would be a 3 by 3 matrix with all zeros in it. All right. For this, we're going to say A, B, and C are matrices. And we're going to say M by N, so they have the same same order, same size. And we're going to say C and D are scalars. And our zero matrix is M by N here also, when we use our zero matrix. So our properties for matrix addition. Any matrix plus a zero matrix is the same as the zero matrix plus our matrix. We just get our matrix back. order that we add matrices doesn't matter. So we can change the order when we add. We'll talk about multiplying matrices tomorrow, and there, the order that we multiply the matrices does matter. Addition order doesn't matter for addition. We can group matrices however we want to add them. So it doesn't matter how we group them. If we do scalar multiplication by more than one scalar, C times D times A, we can group that multiplication however we want. So that's the same as C times D times A. So we can multiply beforehand, or we can multiply the matrix by a scalar and then multiply it by another scalar. The scalar 1 times our matrix always just gives us our matrix back. We can distribute a scalar. We can also distribute a matrix. So they just give us our rules for how we add matrices and deal with scalar multiplication. And so with this idea of scalar multiplication and matrix addition, we can talk about doing some matrix algebra. So let me do one example. Just have one example to do, and then we're done. So questions on our properties. Just like properties of real numbers, we just have matrices. The only difference is we're dealing with a zero matrix, not the number zero. All right. We're going to do one example of matrix algebra. We'll talk about another kind. We'll be able to do more with it after we learn about matrix multiplication. So let's say we want to solve this equation. A minus 2x equals B. And we're going to say that A is the matrix 2, negative 1, 4, 3, and B is the matrix negative 3, negative 6, 5, 1. And X is a matrix. It wouldn't make sense to subtract a number from a matrix. X has to be a matrix. So X is going to have to be a 2 by 2 matrix for this to make sense. So if we were just talking about real numbers and just a regular variable X, how would we solve this equation? What would be our goal when we talk about solving these kinds of equations? What's that? Get X by itself. We want to get X by itself. That's the same thing that we want to do here. Get the matrix X by itself on one side of the equation. So I'm going to do that. That's our goal here. So I'm going to add 2x to both sides of the equation and subtract b. So I get 2x equals a minus b. And x is going to be 1/2 a minus b. Well, we know how to do this now. Now we can plug in our matrices. So this is kind of an example of what I was talking about. We treat each matrix as just a single entity until we get down to where we have to treat it as individual elements. So x, our matrix X, is going to be 1/2 of 2, -1, 4, 3, minus -3, -6, 5, 1. So that's going to be 1/2, and make sure I do my arithmetic right here. 2 minus -3, I get a 5. 2 minus -6, I get an 8. Oh, sorry, yeah, see, I messed up already. -1 minus -6, I get a 7. There we go. 4 minus 5 is -1. -1 minus -6. Oh, 5, thank you. 2 minus, well, that one's right. Lots of places to make arithmetic errors in matrices. Let's see, 4 minus 5, -1. Did I get that one right? Yeah. 3 minus 1 is 2. So finally, X equals the matrix 5/2, 5/2, -1/2, and 1. And that would be the solution to this matrix equation. That would be my matrix. So questions on how we did that? So what we'll talk about next time is matrix multiplication, and how that'll allow us to solve another type of problem, another type of matrix problem that will help us when we're solving systems of equations. And what eventually happens is you can do these kinds of operations where your matrices, rather than just numbers in them, your matrices can have functions in them, and you can apply the functions to other types of matrices, and interesting things happen. But you use these rules for manipulating matrices to treat the matrix as one entity rather than a bunch of things all at once. Kind of a nice thing. All right. One more. I'm in the wrong class over here. Page 527. Should be 12. There we go.